Okay, so now that we've introduced the concept of functions, I want to talk about creating functional expressions. And what I mean by that is I want to talk about how to fit a function to a set of data that you have. So in algebra class, if you can remember your algebra days, if you ever took algebra, whatever, in high school or whatever, in algebra class, we're often given a function and then asked questions about it. For example, you might be told that the profit a burger joint makes by selling X burgers is P of X equals 2X minus 75. And then you might be asked how much profit the burger joint can expect to make if it sells 300 burgers, right? In the real world, it's much more likely that you would experience this sort of thing the other way around. So you might notice that when you sold 200 burgers, you made $325 in profits. But when you sold 400 burgers, you made $725 in profits. And then from that data, conclude that if you sell X burgers, you will make 2X minus $75 in profits, right? So it's usually the other way around. In the real world, we're usually not starting with a function and then using it to build data. We're usually starting with the data, and we use the data to build a function, right? So the process of fitting a function to data is called mathematical modeling. It's something that I will probably call mathematical modeling, although your book doesn't really use that term. But modeling is useful for a variety of reasons. You might use mathematical modeling in the burger scenario to predict how much money you're going to make if you make a particular amount of sales, right? So it could be useful for that. So obviously, like any kind of company is going to be any kind of company who's interested in profits, right, is going to be interested in mathematical modeling. Mathematical modeling is useful to track the climate, right, for climate change purposes and things like that. I mean, it's just useful in a variety of ways. But modeling can be difficult. We're going to just barely scratch the surface on mathematical modeling here, and we're going to talk about two types of functions that you can use for mathematical modeling, linear functions and exponential functions. But in general, the sky's the limit. It's like any mathematical function could be used as a mathematical model, and there are infinitely many of those, right? And so it's like, well, how do you determine what's the best fit for the data? And that's not an easy question to answer in general. But in fact, there are mathematicians whose job is to do exactly that, right? And so like they have a PhD where their specialty is fitting functions to data. But we can at least give you like some basic ideas here. And so let's get into it, right? So let's talk about linear functions. Okay, so a linear function is one in which the images, or in other words outputs, increase or decrease by adding or subtracting the same amount from one output to the next. The rate of increase or decrease is sometimes called the slope of the function, and it's how much the outputs change for each unit of increase in the inputs. So for example, if you were looking at a table of values here, this table would represent linear growth because your inputs here are increasing by 1 each time, right? So you're increasing by 1. And your outputs are increasing by, well, it looks like to get from 6 to 11, you added 5, right? And then to get from 11 to 16, you added 5 again. And to get from 16 to 21, you added 5, and you added 5, right? So you're adding the same amount each time, right, to get from one output to the next. That's called the rate of increase, right? So the rate here would be 5. Okay, here's another table that models linear growth, right? So here you're not increasing your inputs by 1 each time. You're increasing your inputs by 2. It looks like 2. So plus 2, plus 2, plus 2, plus 2. Meanwhile, your outputs are increasing by the same amount. Here we increased by 4, 4, 4, and 4. So since you're increasing by the same amount each time, the this is linear growth. Okay? You're increasing by adding the same amount each time. So this is linear growth. But your rate here is a little tricky. So here your rate was 5. That's because for each unit of increase, you increased your output by 5. Here, you might be tempted to say that the rate is 4. But it's not, because you're not increasing by 1 unit on your inputs here. You're increasing by 2 units on your input. So you have to divide by the increase in your inputs, right? So the rate would really be the increase in your outputs divided by the increase in your inputs. Okay? So the rate is really 2 for this example. Okay? Right? So you're going to increase by 2 units for each 1 unit of increase. Sorry, let me say that again. Your outputs are going to increase by 2 units for each 1 unit of increase in your inputs, right? In other words, they increase by 4 units. Your outputs increase by 4 units for every increase of 2 units in your inputs. So in 1 unit of input, you're going to increase by 2 units of output, right? So 4 divided by 2. Now, this last example is an example of nonlinear growth. So notice that your inputs are increasing by 1, but your outputs are increasing by different amounts, right? Here you increased by 2, here you increased by 4, here you increased by 6, and here you increased by 8. So as for the rate, we would say nonsense, right? Because it's not constant. Right? The rate is not constant. So you can't really talk about the rate here. Okay? All right. So now, note that if the inputs are increasing by a constant rate m, as they are in parts A and B, then you can predict the output for any given input x by multiplying x by m and then adding whatever the starting point was. Okay? In other words, if I know that the rate of increase here is 5 and I want to go down to like 20 down on the list, then I could just say, well, I know it's going to be 20 times 5 plus maybe some starting point, right? Because you'll notice that that doesn't really work. Like if I say 2 times 5, I only get 10, right? And my output should be 11. If I do 3 times 5, I only get 15. My output should be 16. If I do 1 times 5, I only get 5. And my output should be 6. But you'll notice that I'm close, right? It's like I'm only off by, like I just need to add 1 to get there, right? Like if I do 1 times 5, and then I add 1, I get 6, right? If I do 2 times 5, I get 10. And then if I add 1, I get 11. If I do 3 times 5, I get 15, and then if I add 1, I get 16, right? And so forth. So my starting point must have been 1, right? So if I multiply x by my rate, and then I add whatever the starting point is, then I can predict any output, right? I can predict any output. So what we write down is we say f is a linear function. If f is a linear function with rate m, then the rule, right, the formula for f of x should be mx plus k, where k is the starting point, right, and m is the rate. So it's m times x plus k. In your previous algebra classes, you may have called this mx plus b, and that's fine too. You could use b instead of k. But anyway, for example, let's find a formula for f of x under the action of the function described in A above. Well, I've kind of given it away already, right? But I said, well, if you take f of x and you multiply x by the rate, that gets you close, but not quite there, right? 5 times 1 is 5. 2 times 5 is 10. 3 times 5 is 15. So I need to do 5 times x, but then I need to add 1, right? Here's another way that you could have done that, though. What you could have said is you could have said, well, I know that f of x has to look like 5 times x because the rate is 5, and then plus k for some number k. Now, if I plug in one of these numbers, I can solve for k, right? Like if I plug in, it doesn't matter which one, but let's say I plug in this one, the 3 and the 16. That tells me that when my input is 3, my output should be 16, right? So if I plug in an input of 3, the output should be 16, right? Well, so I can solve that equation, right? I can say, all right, so I have to solve 5 times 3 plus k equals 16. I need to solve for k. So first of all, I can do 5 times 3 pretty easily. That's 15 plus k equals 16. And then to solve for k, I mean, it's not hard to just realize that 15 plus something has to equal 16. What's the something? Well, it's got to be 1, right? 15 plus 1 equals 16, so k equals 1. If you wanted to do it algebraically, like we did in the previous section, you would say, well, I want to get k by itself. Right now I'm adding 15 to it, so I need to subtract a 15 to get rid of it. And I'm allowed to do that as long as I balance it by subtracting 15 on the other side as well. And then I get k by itself on the left, and on the right, 16 minus 15 is 1, just like we thought. Okay. Anyway, so putting that all together, we would say, all right, so I know f of x was 5x plus k, and now I know that k equals 1. So really, f of x is 5x plus 1, right? And that's my final answer. Okay? Anyway, so this is the idea behind modeling with linear functions. This is how you model with linear functions. Let me give you another couple examples. So this says, examine the following tables and create a formula for each to express the actions of the functions that they represent. Okay. So in part A, it looks like my inputs are increasing by 5. And meanwhile, my outputs, it looks like they're, to get from negative 67 to negative 37, I think you have to add 30, right? And here you have to add 30 to get from negative 37 to negative 7. To get from negative 7 to 23, well, let's see. If I add negative 7 plus 30, that's the same as 30 minus 7. That is 23, right? So yeah, so I'm still adding 30. And if I add 30 again, yep, I'm going to get 53. So it looks like I'm adding 30 each time. Now be careful, my rate is not 30 because the rate is how much your outputs increase for each one increase in your inputs. But here my increases are all 5. So I need to divide by 5, right? So I'm going to say my rate, m, is 30 divided by 5, which is 6. Okay? So my rate is 6. This function is called g of x, right? So we're going to say, so g of x must be 6x plus some starting point k. And I'm going to solve for the starting point k by choosing some number on here. It doesn't really matter which one. I'm going to go with the 0, negative 7, because I think 0 kind of makes things cancel off and makes things easy. So if I plug in 0, I get 6 times 0 plus k, and I know I know when the input is 0, the output has to be negative 7, right? Sorry, let me get my hand out of the way. When the input's 0, the output has to be negative 7. So I know that whatever k is, 6 times 0 plus k has to equal negative 7. So let me come up here. So I have this equation, right? 6 times 0 plus k equals negative 7. 6 times 0 is just 0, and 0 plus k is just k. So that means k has to equal negative 7. So g of x is going to be 6x plus negative 7. Well, adding a negative 7 is the same thing as subtracting a 7. So g of x is 6x minus 7. And you can verify this, right? Like if you plug in negative 10 to this function, you get 6 times negative 10 minus 7 is negative 67. Right? If you plug in negative 5, 6 times negative 5 minus 7 is negative 37, just like you should get, right? So this is the function that does the trick. Okay? This is the function that fits this data, right? So this is the function that models the action of this function, right? Okay. Let's do part B. Part B is a little, well, it's a little harder, but a little easier in some ways. So it's easier because our inputs are increasing by 1. So that's nice, because then we know that we're not going to have to divide by anything. Our outputs, though, notice that they're not increasing. We had 4.1 and then 1.3, and then 1.3 and negative 1.8, so it looks like they're decreasing, right? To figure out how much they're decreasing, we could subtract, because that's another thing, is that it's kind of hard to do that in your head, but if we do 4.4 minus 1.3, we get 3.1. So that's the amount of decrease. And since it's decreasing, I'm not going to say that we added 3.1, I'm going to say that we subtracted 3.1, right? So here we subtracted 3.1. Now if I subtract 3.1 again, so 1.3 minus 3.1, I get negative 1.8. Right? So that's good, because that tells me to get from here to here, I'm still just subtracting by 3.1. And if I do it again, I get negative 4.9. Okay? So sure enough, right, I'm just subtracting by 3.1 each time. And since I'm subtracting by the same amount each time, this is still a linear function, even though it's a decreasing function, but it's still linear, right? So this was an increasing linear function. This is a decreasing linear function. My rate is negative 3.1. Okay, and since the rate is constant, I know that the function is linear, and therefore it has the form. This function is called h, by the way. So since it's linear, it must have the form h of x equals negative 3.1 times x plus some starting point k, which I can solve for by plugging in one of these things. This time I think I'll plug in the top one. So if I plug in 1, if my input is 1, my output should be 4.4. So negative 3.1 times 1 plus k should equal 4.4. Okay, so I've got this equation that I can solve. Negative 3.1 times 1 plus k equals 4.4. Negative 3.1 times 1 is just negative 3.1. And if I want to get k by itself, I need to add the 3.1 to get rid of it. And I can do that as long as I add a 3.1 to the other side as well. And you're going to get k equals 7.5. Okay, so k equals 7.5. So that means that h of x equals negative 3.1x plus 7.5. Okay. And that's that, right? So that's how we fit models, linear models, to data. Of course, these examples they seem kind of like, well, but these are just numbers. Like, what does any of this mean? Well, let's take a look at an example of how you could apply this to something, right? So this says, in a psychological study, one researcher recorded the following times in which a sample of 5 adults needed to memorize a 9-digit sequence of numbers and letters according to age. All right, so this 38-year-old required 29 seconds in order to memorize the 9-digit sequence of numbers and letters, right? So imagine somebody just gave you a random sequence of numbers and letters and they said, memorize this. Right? How long would it take you to memorize it? Well, the 38-year-old took 39 seconds, the 50-year-old took 35 seconds, right? And so forth. The researcher would like to predict the memorization times for another older set of people before actually testing them. Based on the above sample, what would be the predictions for people of ages 56, 65, and 70? Okay. Well, in order to get those predictions, first we should come up with a function that models this behavior, right? So let's see. We're given ages down here, so we want the inputs to be the ages, and then we want to predict how long it takes them to memorize the 9-digit sequence. So let's do it, right? So our inputs are increasing, it looks like, by 4. What about our outputs? 29 to 31, so it looks like that increased by 2. 31 to 33 went up by 2 again, and by 2 again. Okay. So the rate, it looks like our outputs are increasing by 2 for every increase of 4 in our inputs. So the rate, M, would be 2 for 4, right? So 2 seconds for every 4 years. That reduces to 1/2, by the way. Or, you could change it to a decimal and get 0.5 if you preferred decimals. But okay, so there's our rate. So let's call the function that models this phenomenon f. And since our rate is constant, we would say f is a linear function. And since f is a linear function, it must have the form f of x equals rate times x plus some starting point k. And then to find that starting point, I can just use one of these things. I'm going to use the smallest one, the 38 and the 29. So I know that when my input is 38, oops, sorry, I should have a 38 here. So when the input is 38, the output should be 29. Okay, so I've got this equation, 1/2 times 38 plus k equals 29. And let's see what we get. 1/2 times 38 is 19. So 19 plus k equals 29. And I can solve for k. I need to subtract the 19. And I get k equals 10. All right, so putting that all together then, I know that f of x equals 1/2 x plus 10, right? So now it says based on that, what would be the predictions for people of ages 56, 65, and 70? So for somebody who's 56 years old, we would predict that they would take 1/2 times 56 plus 10 seconds to memorize the numbers. So you can punch that into your calculator to figure out how much that is. We would say 1/2 times 56 plus 10 is 38. So we would predict it taking 38 seconds. Whoop, 38 seconds. Okay, what about the person who's 65? That would be 1/2 times 65 plus 10. So 1/2 times 65 plus 10. That's 85 over 2. And let me change that to a decimal. So 42.5. So we would expect it to take them 42.5 seconds, right? See, and this is the power of modeling, because it allows you to make predictions when you don't have data. And maybe those predictions end up being wrong, but at least they're closer than just a wild guess, right? Okay, and then 70. F of 70 is 1/2 times 70 plus 10. 1/2 times 70 plus 10 is 45. Okay. All right, so that's that one. Here's another one. This is not real world, obviously. We're talking about Acme Hardware. Anyway, Acme Hardware Manufacturing Company has purchased a new drill press for $17,000. If it depreciates linearly and is worth $15,000 4 years later, find a function that gives the value of the press in t years after it was purchased. So this time we're not really given a chart or anything, but what we are told is that it depreciates linearly, right? It depreciates linearly. So it's a linear function, right? It's a linear function. We also know that after 4 years, it has decreased in value from 17,000 to 15,000. So with that in mind, we can say, well, we want to find a function that gives the value of the press t years after it was purchased. So we want the input to be years, t years, right? We want the input to be years, and we want the output to be the value. So the value has decreased by $2,000, while the input, the years, has increased to 4 years, right? So the rate is going to be the decrease in value. Now, it decreased by $2,000. So I'm going to say to go from 17,000 to 15,000, we had to subtract 2,000. And it took 4 years for that to happen. So this is our rate, negative 2,000 over 4. So that, if you do that division, I think it will come out to negative 500. Okay? So what this means is that for every year that passes, the drill press is going to decrease in value by $500. Okay? So if we call the function f, right, we would say f of t, I'm going to say t for time, right, t years. So f of t is going to be negative 500 times the number of years plus some starting value, right, whatever the starting value is. Well, the starting value in this case is really easy to figure out because we know that when the drill press is brand new, it costs $17,000. So I'm not even going to bother to do a whole lot of work there. I can say f of t is negative 500 t plus 17,000. And that's all we were supposed to do here, right? If you were thinking, well, that's too easy, I mean, you could do it in a harder way. You could say, well, when t is 4 years, right? So after 4 years, it was worth 15,000. So you could say f of 4 is negative 500 times 4 plus k, and then you know that that has to equal 15,000. So then this way, it's like the same as the problems we were doing before. Anyway. So if you do the multiplication now, you get negative 2,000 plus k equals 15,000. And then to solve for k, you would add 2,000 over to the other side. And you would get k equals 17,000, just like we knew would be the case because that's how much it cost when it was brand new. But anyway, so that's that one. So that's all I have to say about linear functions. Now, not all growth is linear. So let's look at another type of growth, right? In fact, we saw on the first page, right, that not all growth was linear. This was an example of some nonlinear growth. Another type of nonlinear growth is called exponential growth, right? So an exponential function is one in which the outputs increase or decrease by multiplying or dividing by the same amount from one output to the next. So a linear function was one in which the outputs increased or decreased by adding or subtracting the same amount from one output to the next. An exponential function is one in which the outputs increase or decrease by multiplying or dividing by the same amount from one output to the next. So for example, here's some exponential growth, right? So notice that our inputs are increasing by adding 1 each time. But our outputs, well, something strange is happening there. It's maybe hard to tell with the fractions, but notice that to get from 1 to 3, you could think, well, I added 2, but then to get from 3 to 4, well, I think I have a typo here. I think this should be a 9. Anyway, so change that to a 9. But yeah, to get from 3 to 9, so to get from 1 to 3, I added 2, but to get from 3 to 9, I added like 6, right? So obviously it's not a linear growth, but if I think about it in terms of multiplication, to get from 1 to 3, I can multiply 1 times 3 to get 3. And then if I multiply 3 times 3, I get 9. So to get from here to here, I multiplied by 3. And to get from here to here, I multiplied by 3. And let's see if that works to get from 1/3 to 1. If I multiply 1/3 times 3, yeah, I get 1. You can use your calculator to verify that if you're not really up to speed on fractions and stuff. The same thing with 1/9. If I do 1/9 times 3, 1/9 times 3 is also going to be 1/3. So yeah, so I'm multiplying by the same amount each time. Now here's another thing I'll point out to you. Anyway, so this is exponential growth because you're multiplying by the same amount each time, right? Now another thing to point out to you is that you can use your calculator to verify that 3 to the power of -2 is 1/9. 3 to the power of -1 is 1/3. 3 to the power of 0 is 1. 3 to the first power is 3. And 3 to the second power, 3 squared, is 9. Okay, again, you can use your calculator to verify that that's the case. So notice that this thing that you're multiplying by each time, you just take that number and raise it to your input. Raise it to the power of your input, right? And that gets you your outputs. So in this case, we would say f of x is 3 to the x, right? You just you put your inputs in here, and that gets you your output. So this is what exponential functions end up looking like. They're called exponential because the variable is in the exponent now, right? So more generally, an exponential function will have the form f of x equals k times b to the x. And b is called the base. So this number that you're multiplying or dividing by each time, that's called the base. So here's an example. In music, for any particular pitch, the next higher octave is obtained by doubling the frequency of the pitch. So for example, the A string on a guitar is tuned to vibrate at 440 hertz. The A an octave higher than that would occur at 880 hertz, right? So you double it. So let's use the table below to find the function that models this behavior. So for A, right, the A string on the guitar is at 440 hertz. An octave above would be 880 hertz, and an octave above that would be 1,760 hertz. An octave below that would occur at 220 hertz, and below that would be at 110 hertz. And then if you go below that, you end up at 55 hertz, and I think that's the lowest note on a piano. So on most pianos that go down to like that very low A, is an A 55 hertz. And if you've ever hit that key before on a piano, the lowest key, you'll know that like by the time you get down that low, you almost can't even hear the tone anymore because the vibrations are so slow. It just sounds like a pulse. But anyway, so pretty quickly you reach like the limits of human hearing, right? If you go much lower than that. But anyway, we're supposed to use this table to find the function that models the behavior. So notice, right, to get from here to here, you're adding 1, right? And then for each unit of increase in your input, your output is doubling. To get from 110 to 220, you multiply by 2. 220 to 440, you multiply by 2. 440 to 880, you multiply by 2. So you're not adding the same amount each time, but you're multiplying by the same amount each time. Right? So you know that your function So you know that this is an exponential function because you're multiplying by the same amount each time. So this is an exponential function, which means it has the form k times this number to the x. Now the question is, what is k? So in order to figure that out, we just have to plug in some stuff, right? So we can plug in one of these numbers. I'm going to use 0. 0 is always nice. So if I plug in 0, so if my input is 0, I know my output should be 110. Okay, now if you punch 2 to the 0 into your calculator, you'll notice that, so I have this, so I have this equation, k times 2 to the 0 equals 110, and I'd like to solve for k. So to begin with, I'm going to punch 2 to the 0 into my calculator, and if you do that, you notice that 2 to the 0 is just 1. And then k times 1 is just going to be k. So there you go, k is just 110. All right, so f of x is k times 2 to the x. Now, some of you might be tempted to say, well, why don't we multiply those two together? Why don't we just call it, instead of calling it 110 times 2 to the x, why don't we just call it 220 to the x power? And the reason is because order of operations, right? PEMDAS, please excuse my dear Aunt Sally, however you remembered it, exponents comes before multiplication. You've got to do the exponent first before you multiply. So if you were to plug in 3 here, and this would be a good thing for you to test out, right? If you do 110 times 2 to the 3rd power, and you punch that into your calculator, you're going to get a different result than if you punch 220 to the 3rd power into your calculator, right? So it's not the same thing. So don't the moral of the story is don't multiply these things together. It's not the same, okay? But anyway, that's the function. So that's pretty cool. A few more examples. Number 5 says, create a formula to express the action of the function represented by the table below. Okay. So adding 1, adding 1, adding 1, adding 1. Here, ooh, this is tricky. To get from 6 to 24, I multiply by 4. To get from 24 to 96, well, let's see. 24 times 4 is 96. Yeah, I'm just using my calculator, by the way. And to get from 96 to 384, if I multiply by 4, yeah, so I'm multiplying by 4. I wonder if I multiply 3/2 times 4, does that give me 6? So 3 over 2 times 4 is 6. Yep. Okay, so it looks like I'm multiplying by 4 each time. So my base is going to be 4. This function is called g, right? It's called g of x. So I'm going to say g of x. I'm multiplying by the same amount each time. So this must be an exponential function. So it must have the form k times b times this base to the x power. In order to solve for k, I can plug in one of these things. I'm going to plug in 0 again, because I think it'll be helpful for us to notice a pattern there. Right? So if I plug in 0, then the output should be 24. Well, if you plug in 4 to the 0 into your calculator, you're going to notice that that's 1. Anything to the 0 power is 1. Okay? And then k times 1 is just going to be k. So we know that k is 24. So in other words, if you have 0, you know that that's going to be your starting point k, right? The output's going to be your starting point k. And that's something that you can just kind of use. Okay? So then g of x is going to be 24 times 4 to the x power. Okay? So this is how we model with exponential functions. Let me give you a couple applications of this, right? So this first one says, when you put your money in the bank, it accrues interest. The kind of interest that it accrues is called compound interest. And in the real world, I'll tell you that most things like the money in your savings account, your student loans, right? They're going to accrue your mortgage payments on your house. They're going to accrue a type of interest called, or they're going to accrue a compound interest, but the interest is compounded monthly. We'll get into that later on in the course, okay? But for now, let's just assume that we've got annually compounded interest. So if the account has interest rate R, and if you deposit a principal amount of P dollars, then after T years, you will have P times 1 plus R to the T dollars in your account, right? Note that this is an exponential function, right? You have some base raised to some exponent times some starting point, right? So suppose that you deposit $200 in an account with an annual interest rate of 5% compounded annually, and suppose that you don't take out or put in any additional money. Find the function that models the growth of the money in your bank account. Then predict how much money will be in your account after 5 years. Okay. Well, first of all, we're told we don't have to do this whole chart thing like we did up here because we're told what the rate is. We're told that the rate is 5%. So that's R, right? So R equals 5%, right? So R equals 5%. Change that into a decimal, though, before you use it in the formula. So as a decimal, this is going to be 0.05. So remember, you just take this decimal and move it twice. 1, 2. And you've got to have a little 0 there. So it's 0.05. Okay? So we also know that the principal amount, P, the amount that you invested in the first place, was $200, right? So we also know that P is $200. So A of T is going to be P times 1 plus R to the T. So A of T is 200 times 1 plus 0.05 to the T. And you can add that. 1 plus 0.05 is 1.05. So A of T is 200 times 1.05 to the T power. And there you go, right? So we were supposed to find the function that models the growth. That's the function. That's it. This models the growth in your bank account. Again, this is assuming that you don't take anything out or put any additional money back in. Okay? But then it says, then predict how much money will be in your account after 5 years. So A of 5 is 200 times 1.05 to the fifth. Let's see, 200 times 1.05 to the fifth power. That's about, I'm going to round this to the nearest penny. So this is what I'm getting, okay? But I'm going to round it to the nearest penny. So that would be, if I round it to the nearest penny, it's $255.26, right? This number is bigger than 5, so I round this number up to 26. So it's about $255.26. Which is cool, because you only started with $200, and then you did nothing, and it increased to $255.26, right? So that's kind of cool. Okay, one more. The number E. This is an interesting number. It's kind of like the number pi, right? Pi is like 3.14. E is about 2.71828, okay? And this number comes up with exponential functions a lot. For example, in our previous example with the compound interest, if this is the formula for compound interest if the interest is compounded once per year. If it's compounded twice per year, you get a slightly different formula. And if you allow the number of times that it compounds per year to go to infinity, then you get something that's called continuously compounded interest. And the formula for that is this, right? It's A of t equals P times E to the RT. So there's that number E. Okay? In fact, this function has a special name. It's called the natural exponential function. And it can be used to model the growth of all sorts of populations, right? So it can model the growth of money in a continuously compounded interest yielding bank account. It can be used to model the growth of bacteria or rabbits or humans. So let's give an example. In 1900, the population of the United States was 76 million people. Assuming natural exponential growth and a constant annual growth rate of 1.3%, estimate the population in the years 2010 and 2025. Okay, so again, we know that the rate R is 1.3%. So if you move that decimal over a couple times, that's 0.013, right? So that's your rate. The principal amount, P, is 76 million. I'm just going to call it 76, so I don't have to write out all the zeros. And I'll know that my answer is going to be in millions, okay? So the population, the amount of people at time t, is going to be 76 million times e to the 0.013 times t, right? I'm just following this formula and plugging in p equals 76 and r equals 0.13. Remember that e is just a number, and you can find it on your calculator somewhere. Okay. So what are we supposed to do? We want to estimate the population in the years 2010. Now be careful, don't plug in 2010 for t, because this 76 came from our starting point in 1900. So what we really have to do is figure out how many years have passed from 1900 to 2010. Well, from 1900 to 2000 was 100 years, so this must be 110 years, right? So in 2010, 110 years passed since 1900. So we would say A of 110, right? That's 76 times e to the 0.013 times 110. Ooh, 110. Now plug that mess into your calculator. Here's what it looks like on mine, and your calculator is very likely to be different from mine. Okay, but here's what it looks like. It looks like 76 times e to the power of 0.013 times 110. And then I close the parentheses there. So I get 317.581138,586. But this is in millions, right? So in millions. So this would be 317 million, right? Or we could say 317.6. If I round, right, I could say 317.6 million people. Or maybe I could just round to the nearest million and call it 318 million. So it's about 318 million people. That's not far. That's not far off. The current population of our country is about 320 million, right? So that's a pretty good estimate. Okay, what about in 2025? How many years have passed since 1900? We would say it would be 125, right? 125 years passed since 1900. So, A of 125, that would be 76 times e to the 0.013 times 125. Plug that into your calculator and let's see. I'm just going to go back and change this to 125. That's about 385, if I round it to the nearest million, 386 million people. Okay, very interesting. That's probably not as good of an estimate. I don't think we're going to be up to 386 million people 4 years from now. But anyway, so that's that. So that's all I have to say about mathematical modeling.